we go. Welcome everyone to the Ontology Summit 2020. Today is 12th of February 2020. And we're very pleased to have John Sowa speaking today on knowledge graphs for language, logic, data, reasoning. John?
Okay, let's see. I'm still trying to get this stuff downloaded, so could you please just continue talking for a bit while I will just start in a minute.
Okay. Well, we so far we had a kickoff meeting a couple of weeks ago. Last week we had Chaitan Baru, and those recordings are available online on the meeting pages. Next week we're having Matthew West. And you ready, John?
Oh, yeah. I'm typing things and I'm trying to do something so quickly that I keep missing the letters.
Okay. And then
yeah,
on the 26th of February, we're having Anirudh Prabhu. Then on the 4th of March, Paco Nathan. And we have, we also have someone confirmed, Ernest Davis, on the 25th of March. All of the other slots are not actually open. I'm just waiting confirmation to make sure that, so that I can post them. So it looks like all of the slots will, in fact, be filled shortly.
I can't find my own talks. I thought that I had that at jfsowa.com talk/kgn.pdf, and I had that on my other computer, and I can't find it on this one.
Well, it's posted on the meeting page if you go there.
That's worse. I can never find those meeting pages. Well, it's on jfsowa.com talks/kgn.pdf. I had that. I uploaded that earlier on my computer downstairs, and now I'm on another computer. Were people able to find my slides on my web page? That's jfsowa.com /talks/kgn.pdf.
KNG. Yes, I just got it. KNG.pdf.
KNG. Oh, right. I keep typing KGN. Sorry. Thank you. Okay.
John, you should banish acronyms.
Okay.
While we're waiting.
Okay. Yeah. I'm really sorry for this. I was doing everything at the last minute. I finally got my slides finished this morning, and then I'm just running around. Okay. Anyway, I finally have my slides in front of me, so I'll just read off the slides, and then the first one is I'm talking about knowledge graphs and the relationship between language, logic, data, and reasoning, and all of the issues that have been going on with the semantic web and with the work on knowledge-based systems and all the databases and knowledge bases and how everything ties together over the past half century or so. So the first slide, or that's slide 2. That's the one that gives a brief summary of the history. And the point that I keep mentioning is that all the basic work on data representation and formatting was done with punched cards. And there's a very simple transition from punched cards to the computers. And so that as soon as computers became available, all of the banks and businesses were able to take their punch card systems and instantly, well, not really instantly, but very quickly map them into Fortran, Lisp, COBOL, ALGOL. And in fact, COBOL is very directly designed so that each punch card represents what they called a unit record, and the record structures in COBOL are designed to map directly to and from COBOL. And in the 1960s, when they started up with the database systems, they were designing the databases in such a way that they mapped directly to and from COBOL and the other programming languages and all the punch card and the paper tape stuff that had been developed over the years. And in fact, the IMS database system, which is based on records, every record in IMS maps directly to a card, although after they went beyond, when they went to tapes and disks, they went beyond 80 characters, but the idea is very much the punch card kind of data. And in fact, when you get to relational databases, you have tables in which the tables themselves represent the kind of things you have in punched cards. So you can see that how the database stuff from the original Hollerith machines designed for the 1890 census, that those things carried all the way through to the computer systems of the 1960s, and we're still living with exactly those same kinds of formats at the foundation of the systems we develop today. Now, in the 1970s, there were all sorts of new database systems that were coming up, and there were three main directions. One was the original hierarchical databases, that was IBM's IMS, and the network databases, which were being developed by several other companies. And then there was the new relational databases, which were based on logic and using logic that maps to and from formats that are similar to the kinds of formats they had from way back in punch cards days. In the 1970s, there were the database wars between your one system or another, and that was sort of ironed out by the 1980s with the conceptual schema and for knowledge bases and object-oriented systems. In the 1990s, we had ontologies and statistical systems and machine translation. In the 2000s, that's when we got the semantic web, very large ontologies, and people saw the need for standards. Well, in the 2010, that's when we got the 2010s, we got really big data, just huge amounts of data. The deep neural networks, which have proved to be very useful for perception and pattern matching, but nobody has yet had a universal ontology. There were proposed standards for ontologies, but basically what those proposals did is give us multiple silos. So everybody who has, each top level represents a different silo, and then you have problems of trying to relate those silos to one another. Now, the question is, in the 2020s, what can knowledge graphs do? How are they related to all the above? In what ways do they differ from all of the above? How do they differ, and why do they differ? And those are the issues I'd like to just talk about today. Okay, now on the next slide, there is the knowledge graphs, and I borrowed this slide from Kingsley Edain, who had a nice diagram that I liked. And at the top level in blue, it shows a graph of that shows a kind of a schema level graph. It represents an ontology that defines the classes, properties, and relations, and that's the graph in blue. And that graph in blue relates to the actual data that can be represented in your database, and this can be, billions of tuples or relations or whatever. And there you can have your knowledge graphs, which represent the instances. So for the ontology level, this describes the pattern and the actual instances that fill in the pattern with the actual names of the people and places and things are the one in the orange level and the second level. And then down at the bottom is the source data, and there you have graphs, knowledge graphs that are derived from various kinds of documents, and some are things that have already gone through some processing, such as DBpedia and others. But that source data can be in the immense volumes to the terabytes and whatever and more of data on the World Wide Web and elsewhere. Now, the idea is that the knowledge graphs can be used in a variety of ways, and this illustrates the three kinds: the ontology and the definitions, the database instances, and then there's the source data in your documents. Now, the next slide shows another one that I picked off the internet, and this is from an article on building the LinkedIn knowledge graph, and the authors of that article discussed the knowledge graphs for Microsoft and LinkedIn. And these two graphs represent, this is on slide number 4, and these are the two graphs that represent the knowledge, the Microsoft graph, in which you represent things like your calendar, your expertise, your customer accounts, the contacts, meetings, messages, documents, collaboration, email, and so on. This is a graph that Microsoft uses for filling in the instances for all of their clients and so on, and the software that they're using. And then on the right is the LinkedIn graph that LinkedIn uses for relating the stuff that they store about their clients. And there you have prospects, recruiting and hiring managers, learning, jobs, insights, universities, coworkers. Now, this is a rather these graphs are kind of low-level details, and there's an immense amount of more information that would have to be represented about them. But this gives you the basic patterns and then of the knowledge, which can then be filled in detailed knowledge graphs that have the that for each individuals. Now, the point on this is that the labels on these nodes are arbitrary. And notice that there are no labels on the Microsoft graph that are in common with the LinkedIn graph. On the other hand, a lot of people will be using both Microsoft technology and LinkedIn, and they need to relate these things. And this creates a lot of problems of how do you relate knowledge graphs that conform to different patterns and relate them to one another and to the documents from which they're derived. The point is that the knowledge graphs are more informal. There are fewer constraints on the source of data, the uses of it, and the relationships among the nodes. And you can click on that, the title in blue, Building the LinkedIn Knowledge Graph, and that'll take you to an article that discusses that. Now, the next slide, this is, okay, now, yeah, the next slide talks about the conceptual schema work from the 1970s and 80s. And this graph is, and this graph on the diagram on the left, it shows the ANSI Spark architecture. This was defined in a technical report in 1979, and this was widely used in databases during the next 20 years or so. Unfortunately, the technical report by ANSI never made it into a standard. And then ISO had a technical report that never made it to the standard level in 1987. And there were various standards projects that ended, another project that ended in 1999 as a technical report. People were trying to develop standards for the conceptual schemas. And if you look at the diagram on the right of that picture on slide 5, it shows the conceptual schema in white in the middle. And that corresponds to what we call an ontology today. And there are the overlapping circles, and in the red circle, it shows the database, and there you might have a database schema for any kind of database. And if you look at the diagram on the left, it shows under the internal schemata, it shows 3 kinds of databases. One could be a relational database, another a network database, and another hierarchical database. And the idea is that exactly the same conceptual schema can be used to interpret data from any of them. And this is a point that I keep emphasizing, is that ontology is independent of any language or representation. The ontology depends on logic, which can be represented in graphs or linear or tables or anything. You can represent a logic in a variety of different forms, and in every form it's identical, logically identical, but there may be differences in the performance and access and the algorithms. And so the idea is of the conceptual schema work was to allow the implementers to choose any mechanism or any notation or representation internally for the internal schema, which represents how the database stores the data, is totally independent of the ontology. It depends entirely on the algorithms that process that and optimize it for one purpose or another. But the conceptual schema, which represents the ontology, is totally independent of any storage method of any kind. So it's irrelevant whether it's a graph, a linear, or a table. All of that is totally irrelevant to the semantics. And then on the three schema architecture, the external schema represents the linkage, the APIs that go to the user's software at the top. And these standards projects for the conceptual schema pretty much ended around 1999, largely because the semantic web co-opted all of that, and that became the next great hope for unifying the world. And if we go to slide 6, that shows the DARPA agent markup language. This is the presentation by Jim Hendler, who was the DARPA project manager at the time. And he is the one who wrote the specifications or wrote the requirements documents. And the winning proposal to propose for implementing this was by Tim Berners-Lee. And so if you notice this diagram on slide 6, it talks at the top about higher order logics, HOL. It talks about fuzzy logics and vagueness and all that, and then a MEL that combines these things. And then there is this level, classical logic interchange level, and that is supposed to be the level at which you interchange information among any of them. And then underneath that is the supporting technology that supports it, and underneath that is RDF, which we have seen the triple notation, and then XML is the notation for representing RDF. And I would say that the biggest mistake on this diagram is XML. That the idea of standardizing the syntax before you standardize the semantics is the biggest mistake that was made by DARPA, and it was also strongly influenced by the success of the semantic web. But the idea is that the semantic web became successful because people were interchanging, needed a common format for interchanging data at the operation level, and that's TCP/IP and HTTPS. That's what made the semantic web so successful, and the predecessor to XML was the one that, the HTML, that gave people a standard way for representing diagrams and pictures and everything else. And so that was very successful for interchanging stuff, but the idea of using syntax as the foundation for semantics is the single worst mistake that was made by the DARPA people, and it was the single worst, and it was influenced by the emphasis on the syntax for XML, for the semantic web. And on slide 7 shows the layer cakes for the semantic web. Now, on the left is the proposal, the winning proposal by Tim Berners-Lee, and that's the one that is very close to what Jim Hendler had in his proposal, and it has this big yellow arrow. The double arrow at the top is the semantic web unifying language for classical logic, and it supports at the top conversational interfaces, heuristics, search engines, and non-classical logic. So the idea was that you would have an open-ended variety of modal logics and fuzzy logics and all sorts of stuff above this interchange level, and then below that are the various things that support it. And unfortunately, at the bottom is XML, which was pretty much people found that okay if you're embedding stuff in a document. On the other hand, if you want to just write a lot of stuff, the JSON notation is a lot more convenient, and you have this whole bunch of different other notations that sprung up after that. And the whole idea of XML was to have a single unified notation, but the problem is that XML was so unwieldy and unreadable that it caused a new generation of a wide variety of different languages. And then the system as delivered in 2005 is a very poor implementation of the requirements by DARPA or the original proposal. And notice that there's just a mess of different notations there: query language, Sparkle, RDFS, and then role language, and then there's this idea instead of this unifying language being the knowledge bus at the top, there's just this little box called the unifying language, which is somehow unifying logic, which is somehow supposed to relate all of them. And the problem is there that what was delivered in 2005 was better than nothing, but even Tim Berners-Lee himself realized this was just the first step, and he wanted to get a lot more work done because this was only the first step, and it really didn't unify things. And the idea of building semantics on top of syntax was not the best idea. Well, this leads to the future challenges and possibilities. This is slide 8. And the idea that knowledge graphs are much more readable and flexible. Now, one of the things that was the worst single decision for the DAML project that ended in 2005 was decidability. And Bob McGregor, who had been developing various description logic systems, the biggest one in the 1990s was Loom, which was very widely used. And Bob said that users never, ever ask for decidability. They always want more expressive power. They never want decidability. And the idea of decidability is that you could, in polynomial time, prove that your system was, that your ontology was consistent. Now, the serious mistake with that is that you never want to have a test to verify that your ontology is consistent after the fact. What you should have is a methodology in which you design an ontology that is guaranteed to be consistent, and because it's automatically generated in a way that guarantees consistency. And that's the crucial thing that was the mistake with the semantic web, is the idea of trying to prove consistency after the fact. What you really want is a system that will generate consistent systems before the fact, guarantee that you're always going to be consistent. So the idea is that you want to explore new technology developed in the past 15 years, and you want a humanly readable notation, you want flexibility. Decidability is totally meaningless. That's the worst mistake that was made in OWL, is to put in all kinds of kludges. What you really want for your hierarchy is a very clean, simple ontology that is automatically derived in a way that is guaranteed to be consistent. And the idea of decidability to prove that it's consistent after the fact, that's a dead end. It's a deadest of dead end. So the point is that you do want better notations, you want them more flexible, you want them to tie into new technology that's been designed in the past 15 years. And the point that I make, the bottom line, it's premature to specify a standard since the range of possible technology and applications is still in flux. We don't really know what we are going to want in the next 15 years. And if we just look back what happened in the past 15 years, it was a disaster. I wouldn't say it's a disaster. There's a lot of good stuff that has been done, but the fact that ontologies aren't being used every day and in every possible way means that there were some mistakes along the way, and we should try to avoid those mistakes in the next 15 years. Well, that last slide 8 is my conclusion, and I want to go on slide 9 to what do we mean by the challenges and prospects and possibilities. And so slide 9 shows in the middle, it shows common logic. Now, common logic was originally designed by Pat Hayes and Chris Menzel, and then I joined them after Pat and Chris started the thing. And the idea was to have a common notation that would satisfy what Tim Berners-Lee had in that semantic web language. And the idea of the semantic web language is one that is upward compatible with RDF and one that can be used to support an open-ended variety of languages and systems. And so that's where we were working on common logic. Unfortunately, what happened is that the people who designed OWL did not like common logic because it had too much expressive power. And so they went their own way and they designed OWL independently of common logic. However, it can be compiled and translated into common logic, but that's another story. But the idea of common logic is to have a very expressive language in the middle with several different implementations and graph notations and XML notations and more traditional kind of notation. And then above that, above the level, you have human interfaces where you have controlled natural languages like controlled English, Chinese, Spanish. And then you have various diagrams, your UML diagrams, topic maps, concept maps, and various diagrams that mix the two, that mix text as well as diagrams. Then underneath the common logic, then you have an open-ended variety of systems that process that in many different ways. You have SQL and OWL and Datalog and RuleML and Prolog and RDFS. All these are implementation levels that no human being should be forced to use. Now, that some people do use those. Those are the system programmers who dig into the innards. But the languages in pink at the bottom, 99% of the users should never even see those things. Those things are underneath the level. Most people, including people who are experts in their own field. So for example, somebody may be an expert in physics, but they are not an expert in medicine or an expert in sociology, and they want to be able to use the system in their ordinary native language. They don't want to have to learn a totally new language for every specialty they use. So they want to be using the human interfaces. So people that are specialists in one area will still want to use the same human interfaces that are used by people who have never gone beyond, say, a high school level. And we want to be able to let people at every level be able to use some variant of the human interface. Now on slide 10, this talks about the distributed ontology model and specification language, abbreviated as DOL. And this has become a standard. This is a standard of the OMG. And the idea is to provide tools and methodologies for mapping all of these logics to and from one another. And in the diagram on page 10, at the bottom is CL, that's common logic, and all of these various notations, let's see, well, F logic is an exception, but F logic is almost maps into it. It maps into it indirectly, but it can be mapped into common logic. And then there's these other versions that all map into one way or another. They map into common logic as this very general notation that can be used to represent all of them. Now, this is a diagram that shows some of the interfaces at an earlier stage. And if you go on to the next slide, they increase this and it shows a whole bunch of other languages that have been developed since then. And all of them are supported by the HETS system. That's the heterogeneous, I forget what T is. Heterogeneous task, I think task specification or something. And the idea is that HETS is a technology that can be used to translate one notation to another. It specifies all these notations formally, and it can map them all from one or another, and eventually ending up in common logic, which then maps into CASL, which is their implementation language, and that's a subset of the most general higher order logic, which there are higher order aspects to common logic and others there, but the most general HOL is one that is so unwieldy that nobody really implements that for practical computation. But the idea there is that all of those languages can be and have been translated from one to another, and the HETS toolkit, which is freely available, open source software, can be used to map all of these. So the idea is that logic is the foundation of all the semantics, and by the way, we also want to include fuzzy logics. That's not mentioned here. You want to include fuzzy logics and probabilities and the others that were mentioned in the requirements document. This is Jim Hendler's requirements document for DAML. They wanted a lot more flexibility. They wanted to be able to handle vague data and vague representations and probabilities and error estimates on their reasoning. That can be represented in common logic, but that would be at a meta level notation, which can relate any statement to probabilities and so on about that notation. But the idea is that you want to be able to put all of this technology beneath the level that 99% of the users would ever see. They never have to look at this diagram on slide 11. They should never have to deal with that or even think about that. Unless, however, they get into the details where they're doing the theory and implementation. Now I keep mentioning that what you should do is have a system that automatically generates your ontologies. And one of the mechanisms that has been developed to a very high extent and is widely used also to verify OWL ontologies. And this is formal concept analysis, FCA. And this is a theory that has supporting algorithms and methodologies, also freely available as open source. And the idea is that what you do is specify your ontology. You describe your attributes by, for each concept by a list of attributes, and then you dump all of that information into the algorithms and into FCA, and FCA automatically generates a complete and consistent ontology, a hierarchy with multiple inheritance. And people often say, oh, you don't want multi-inheritance because people might make a mistake and accidentally create errors. Well, that is true, but the idea is that FCA is not done by, is an algorithm that is guaranteed to generate a complete, consistent multi-inheritance ontology. And the idea there is that the humans just say for each concept or each word that they're defining, they list the attributes, the plus and minus attributes, positive or negative attributes that it must have. Those attributes can be the properties and a wide variety of different kinds of things that you want to say about your concept. And you just say for each concept or type, you have a list, true or false list of the attributes that apply to it. And then you dump all that into FCA, and it comes out and automatically generates a hierarchy and a lattice that is guaranteed to be complete and consistent. And you don't have to prove that it's consistent because it's generated to be consistent. And there's the references. There's the FCA homepage. And for an examples, you can go to, it also has some examples that you can look at. And then on the next page, it shows this is generated from Rogets Thesaurus. They have two examples there. One is the lattice generated from WordNet, and another is a lattice generated from Rogets Thesaurus. And what you can do is you can type in any word, and then you'll see the hierarchy around that word. And so if you go to that website, there's the bottom, it says where you can find it. You just type your word happy, say the word happy, and this gives you a little lattice that is the excerpt from that big lattice that shows all the words related to happy. It shows that coming from the top, you have the words elegant, agreement, foreboding, and willingness. And then under that, you have under the elegance and agreement, you get neat. And under neat, you get that neat and timeliness give you felicitous. And felicitous is one super type of happy. And then, so happy is a combination of joyous, felicitous, or cheerful. And that's the way that Rogets Thesaurus would define happy. And if you want to see how the subparts are defined, you can just click back and say that that neat is a subtype of elegance and agreement, and cheerful is a subtype of foreboding and willingness, and happy is also a subtype of pleasure. And so this gives you a little lattice generated automatically from whatever data or source you got. In this case, Rogets Thesaurus, another one is WordNet, but they have applied this technology to concepts with hundreds of thousands or more concepts in your hierarchy, and it automatically generates a lattice with multiple inheritance that's guaranteed to be correct. You don't have to worry about proving that it's correct because it is guaranteed by the way it's constructed to be correct. And also, it's constructed automatically. You don't want to have people laboring away at trying to create a 100,000 node hierarchy. The system will, you just push a button and it takes a few seconds and you've got it. Now, another point about it is you want your knowledge graphs to describe things in different ways. And the question is, here's a little structure of blocks. And how do we describe it? There's a wide variety that ways you might describe it in ordinary language, and there are multiple languages and multiple options in each language. And how do you define it in some version of logic? Many different logics, and how do you describe that? Or in a relational database, or the semantic web, or in a programming language. And then the point is, if different people describe the same object in different ways, how could you find out some way of relating this? And this illustrates the point about structured and unstructured representations on slide 15. It shows how we can describe two structures in a relational database where we have two relations named objects and supports. And then we have another way of describing it. In English, we have a sentence that says, a red pyramid A, a green pyramid B, and a yellow pyramid C support a blue block D, which supports an orange pyramid E. Now, the point is that this English sentence and those diagrams, those tables, are related in the sense that they both come from the same structures, but they are really very hard for people to see how they're related. And this is an example from technology that we had in an earlier company called VivoMind. And this shows how you can map the English sentence to a conceptual graph. This is one type of semantic network that has a mapping to and from common logic. And that's on slide 17. And then on slide that's slide 16. On slide 17, we have another two little types of graphs that map to and from the database relation, so that for each line of a database, you can map that to a conceptual relation for a conceptual graph. And so for every row of each of the databases, you get little conceptual graphs like that. And the point is that those little conceptual graphs derived from your SQL tables can be put together to form a bigger graph. And this is a graph that represents concept nodes as represented in the SQL table. And they also represent that same little structure. And this is on slide 18. Now on slide 19, we show that we have two different graphs. They're very different in structure, and one maps, the one on the left comes from natural language, English in this case, and the one on the right comes from your database, and both of them are graphs that represent knowledge that describes that same structure. The question is, how can you relate these two very different structures that use different ontologies? How can you know that they both represent the same structure, therefore there should be some mapping between them. How do you do it? And this is an example that I used in my knowledge representation book that I wrote in 2000. And this is presented this as a problem, and I stated that this is a kind of problem we have in interoperability. Here we have the same structure that two people viewed from different ways for different purposes. One person mapped it into English, then to logic. Another person mapped it to a relational database and then to logic. And if you map them in a graph, you see very different structures. Well, it turns out that there is a transformation from one to another. And this was a technology that Aaron Majumdar developed, a colleague of mine. He designed this VivoMind analogy engine, which does this mapping automatically. And he had never tried this out. And I said, here's an example in my book. Can your system do this? And he did this in, this one is when we were talking in 2001. And he said, well, I never tried it, but let me see. He typed both graphs in a linear notation and then pushed a button, and it took a couple of seconds, and bingo, it found this transformation, and this transformation gives you an exact mapping from one graph to another. And this is the kind of thing that's possible, and I believe that this is the future direction for all of these kinds of technologies. We have to automate everything as much as we can, and this is not, you can't really call this true AI. This is the supporting technology for artificial intelligence, which can be used to make all of our interfaces simpler and easier for humans, so that the systems can talk to people in their own native language, but internally they can do all of these computations that are guaranteed to be correct, and no human being really has to dig into it. Now, the system programmers will have to dig into this in order to implement the tools, but the average developer who's using these things can talk to these systems in ordinary, read and write and talk to these systems in ordinary language. Now, this gets into another issue about language, and that is context. And here's this cartoon from High and Lois, and the boy says, if you can tell me what kind of cookie I have in this box, I'll give it to you. And the girl says, chocolate chip. And he says, right, here's the box. And the girl screams, Mom. And the point is that there are these pronouns like it. I'll give it, if you can tell me what kind of cookie I have in this box, I'll give it to you. Is that the cookie or the box? So she says chocolate chip, and she ends up getting the box. Now, that's the problem that occurs constantly in language. And these are the issues that are very hard for computers to analyze. The neural network systems still do not do pronouns very well. They don't handle these things very well. They are beginning to do some things, but usually they're just at a local level, and they can't handle the pronouns that can cover the entire document, where you have concepts that might be defined somewhere in the beginning of your document, and then they may be underlying everything else that goes on throughout the document, and the words that refer to the original definitions might never appear again in the rest of the document. However, the structures that were defined right at the top will control everything that is said in a 20 or 30 page document. And that's the problem that we have, that current systems really don't handle very well. Now, here's another example using the context for language understanding. And this is on slide 22. And it shows this is one of the shoe cartoons. You can find that by searching for moving at their shoecomics.com. And there is everything in the shoe comics are birds. So the one bird on the right has a car and comes in, and the mechanic, and he asks the mechanic, what's it going to take to get this thing moving again? And then the other one says, parking on a hill and releasing the brake. Now, analyzing the syntax of those two sentences is trivial. Almost any natural language technologies today can map those two sentences into a parse tree or whatever. That's correct. But how do you relate it to this picture? Now, if you look at the picture on the left, we can see that this is kind of parts of a car with its hood up, but that's not the kind of thing that any of these neural networks have been trained on. Very few of them are trained on cars with their hood up in a garage. And it's very, very hard for any neural network to recognize that as a car. So it says, what's it going to take to get this thing moving again? What thing is the guy on the right talking about? The guy on the left looks like a workman working on working clothes, and so he's looking at something. Now, what is it moving? Does it mean that he's looking at something in that dark pit under there that's moving, some part of the engine? And even if you know that this is a car with engine, does it mean that some part of the engine to get moving? And then on the right, you can see a little bit more of the car, and it's in a garage. But again, the pattern matching today is very hard to recognize that this is going to be a car in a garage. And then the guy on the left says parking on a hill and releasing the brake. Now, the brake of what? Well, if we know something about cars have brakes, and we know, and then parking, they could also be parked on a hill, so that relates to cars. But then we need to know something about physics about cars on a hill, and about releasing the brake allows a car to roll, and that would make it move again. Now, these are issues that no computer system today can really understand. Yeah, when you see these publications where they do all kinds of wonderful stuff, those publications are written by people who have solved one particular problem, and that problem looks very impressive, but that problem is just an isolated piece of the totality. And when you just look at these cartoons, you can see how many different pieces have to get put together in order to understand just this one little cartoon. And this is a cartoon made for kids. I mean, well, adults can enjoy it too, but I mean, children understand these things, but adults can understand them even better. And sometimes there are others that children understand better than adults, but that's another story. But the point is that this is the kind of problem we have today with language. And we have all these issues that how do you recognize the situation type, the roles of the participants? How do you rate thing to the car? And then when it says, what's it going to take? How do you, to get it moved? How do you represent, what does take mean? Now, take has a wide range of meanings. If you look up take in one of the large unabridged dictionaries, you have a long, long list of meanings. And how do you know which word sense of take do you mean? I mean, it's not going to take, do you mean take it money? Well, that's exactly, that could be what it means, take, that the mechanic is going to ask for money, and so the mechanic is going to take some money from the guy on the right in order to fix the car in order to get it to move. But none of that information is in that diagram, and that is the problem that we still need a lot more work to handle these things, and maybe we'll get them done in the next 15 years, maybe not.
Okay, John,
Now, then,
I think it's a good point where we should move to the discussion phase.
Okay, good. That's fine. I have now, as I said, slide 8 was my conclusion, and what I've then done is to move on to a variety of different issues. So if there are any questions, please raise them.
Robbie has his hand up.
Yes, my couple of observations in your slide. By the way, very good presentation, John. But on your slide 3, you have all our title slide. You have everything except search and
well, okay.
any reason
Well, your
are secondary
voice is breaking
attributes.
up. Your voice is breaking up. So what are you trying?
Kindly go to the slide title.
Okay. Okay, so we'll go to slide 3, and I put on slide I put knowledge graphs as the title. And so what more do you want there?
There are adjectives that you describe. I will go to that slide myself. I've downloaded.
John?
You say language, logic, data, and reasoning.
Oh, that's on the title.
But knowledge graphs are also for search and discovery.
Search and discovery, you know, yes, sure. Okay, there's a lot. I wanted a title that would fit into there, but search is part of anything that does reasoning, that does language. You know, you want to find things, and so that's just so obvious. And discovery, well, discovery is one of those things that I would say that's in the future. And there are search and discovery. Well, yeah. The example that I had just talking about discovery, just look at that example that we just had about the cartoon of the guy who takes his car in for to get it fixed. Trying to understand those two sentences, the sentence by the man who brought the car and the sentence by the mechanic who's examining it, that you need a huge amount of search and discovery to answer those. And yes, but you know, I mean,
that is the complication arising because we are using natural language. But there are a lot of data structures and database entities which are related to each other in a logical fashion, and people are discovering results using those. Using knowledge graphs.
The issues of searching and discovery, this is all part of reasoning. And under reasoning, I include informal and formal. But the point is that the reasoning is an open-ended variety of things, and it's not really going to be done just by any kind of notation. A notation of knowledge graphs is basically just one more notation for some subset of what's in your language and logic. And there's nothing in the knowledge graph that does anything more than what you could do with the graphs that we had 20 or 30, 40 years, 50 years ago. There's just another notation, and the main thing about knowledge graphs is that they are designed to handle huge amounts of data, and they're designed to handle, you know, like up in the billions, and they're designed to be used in systems that are combined with all of the latest technology. And what I'm trying to say in this talk is that there's that technology that we're developing today is based on the same kind of technology that we had for, well, actually since Aristotle. In fact, Aristotle's 4 sentence types for syllogisms are sufficient to represent the basis for any kind of hierarchy. And then there's features of OWL that aren't in that go beyond Aristotle's 4 sentence types, and those can be represented in first order logic or in if-then rules. And I would say that one thing that you would have for defining your logic is your knowledge base as represented in your hierarchy, your ontology, and then if-then rules, and that's your formal stuff. Now, the next thing you have to do is discover patterns, and that's where these neural nets have proved to be very useful. But the problem is, what patterns are they discovering, and how do they discover them? And if you just look at that example of the 2 examples of the high and lowest cartoon about the chocolate chip and the box, that's something that is still a difficult problem to do today, and some of them are getting better and better at handling references that within a sentence level, but trying to do references that cross an entire document, as we have a 30-page document, trying to find implicit references based on things in that. These are research issues, and to say that knowledge graphs are designed to handle that is just saying that there's a hope that someday they will do that, but you know, that hope is still, I'm saying that's still a challenge to be done.
Okay, on slide 3, you are mentioning 3 things about knowledge graphs: ontology, databases, and source data.
Right.
But the result of using in 3 ways, in these variety of ways, is to reach at some sort of answer to a question or answer to a follow-on
okay,
question.
Sure. Well, sure. Yeah, of course. I mean, I copied this diagram from Kinsley Edayan's page, and you can go to that and look at it. And he talks about a lot of these issues, so go look at that. If I put every issue on every graph, it would be totally unreadable. So the point is,
Sure.
though these get into the issues of the challenges and the challenges, which are still research issues that are still, when you talk about, are they solved? Well, yes, the technologies that were developed 40 years ago, they had expert systems that answered a lot of these questions. However, each of these expert systems was designed to handle one little problem very, very well. And the problem is, how do you extend them to a larger range? Well, today, the idea of these knowledge graphs is to handle them, go beyond a single page to something that's more like pulling data out of multiple documents across multiple stages. And that is still a very much of a research project. There are things that solve it, but this belongs in the challenges and questions and opportunities that have to be developed in the next 15 years. We don't have a solution to them today, but this is a hope rather than a solution. Okay, well, if there are other questions.
Well, nobody else has their hand up, but Doug Miles had a number of comments.
Yeah, if there are comments on the chat room, maybe some of those are comments. I haven't had time to look at the chat.
Kenneth?
Todd?
I just put my hand up. Sorry, I was slow.
Okay.
John, quickly, well, you'll probably have an answer after I have to leave because I have to go to another meeting. It wasn't clear from your presentation, how do you view the current use of ontologies with knowledge graphs?
Well, I would say that basically what they have done is made knowledge graphs simpler and more flexible and in many cases more vague.
Right,
and
I realize.
So that they're approximations. So the basic thing is that there's nothing new that they have with it. They are just right now at the stage where they're relaxing the constraints. That what was done for the semantic web was to have it absolutely precise. The goal of the OWL people was to have absolute precision, and they put restrictions on it to limit what you could say because they wanted to make it more restricted so they could only solve a limited number of problems. And what happened is that you wanted to make it broader and simpler and with a much, much broader range, but these things are still research issues. And one of the things that they have shown is that for many cases, the pattern matching that is done by the semantic web, or by the deep neural networks, has been very useful in handling things that that can't be done that well, or that we still haven't been able to solve by direct reasoning. However, what they do is by using immense amounts of data, they can find patterns that that are buried in all that data. Now, that's very, very good, but notice that they're not doing it the way people do. People, even a 3-year-old child, can do some very, very clever discoveries and reasoning without that immense amount of data.
John, what I meant is, in your graph, the one you're showing, the slide you're showing right now, number 3, you say knowledge graphs may be used in a variety of ways. But what I was getting at is, what is your view on the need for an ontology if you're using a knowledge graph in an application or a system? Should people just go willy-nilly and use whatever labels they want with no thought as to the ontological implications of what they are using or doing?
No, well, the point is, notice those three graphs, the one at the top, that's the definition. And this says that if you're using this particular application, that top level is the ontology, and it handles those things very well. Or look at at page 4. There's a knowledge graph for LinkedIn and a knowledge graph for Microsoft. Now, if you're using Microsoft technology and you see the labels on those nodes, Microsoft has designed software to handle everything that is labeled on that node, but the Microsoft software is different from the LinkedIn software. And if you look at the LinkedIn graph, the labels that they have. So basically, their LinkedIn graph represents the kinds of things that their LinkedIn application software knows how to deal with. The Microsoft graph describes the kinds of things that the Microsoft graph knows how to deal with. And if you use a graph that doesn't fit, it just doesn't fit, and the system will come back and says, I don't know.
Yeah, but then you just that example just suggests that the requirements and the scope of their application are different and are limited.
Right, and so the schema, basically the point I make is that this is very closely related to the conceptual schema idea from the database field in the 1980s. And the idea is that every application, for every system of applications, it might cover a wide range of different but related applications. So let's say if you go to Shell Oil, Matthew would have an ontology that would cover all of the words that would be used in the various applications at Shell, and they would map to the conceptual schema for the Shell databases, and that's in their ontology. You know, there's no magic with these graphs. The knowledge graphs aren't doing any magic. They're just relaxing some of the constraints on this strict logic thing so that they can sort of squirm around things, and they can handle sentences that don't have every last one of the connections in, so they'll do approximate matches. So basically they're doing approximate matches, informal matches, to try to do the best they can to answer the user's query. And whereas if you type the things into a strict reasoning engine, the kind of things that OWL does or that a strict first order logic thing does, if it can't do something, it'll hang up and says does not compute or something like that. Whereas the idea is with your knowledge graph is always to say something helpful and maybe carry on a dialogue with the user so that the human and the user together can carry on a dialogue to work their way around to find out what they're trying to look for. Now, I think that's where the discovery comes in. The best discovery, the problem about queries is that usually they were designed for just a one-shot thing, that you ask one query and you get one answer. And the idea is that you really don't want a query, you want a dialogue where the human and the computer can jointly collaborate in exploring the knowledge base and honing in on what they want. Is that okay?
I think John had to, Todd had to leave, John.
Okay.
So
I think that's the point.
Well, Robbie has his hand up again. We really have to finish the meeting. People are leaving. We've run a little over.
Just a quick one, you know, the big question people are asking on chat is about the substrate for starting not being the syntax but being semantic. How would a scenario developed if that had happened?
Well, the idea is that to understand a knowledge graph, you don't use strict parsing. Well, you do need to do some kind of parsing of ordinary language, and you do have to recognize nouns and verbs and their connections. But the idea is that the primary guidance is not from the syntax, but from the semantics. And so if you look at the graphs on page 4, slide 4, there you see a Microsoft graph and a LinkedIn graph, and the labeled nodes there are the critical semantic issues that are dealt with by the applications from those two companies. And those two companies are designed to handle different kinds of applications, and they're designed around the labeled nodes on that graph. And so that if you say express a sentence that has an approximate mapping to one or another node on those schema graphs, then the system can carry on a dialogue and say, well, I know here's something that I know about it. Is this what you're looking for? And then carry on a dialogue where together by follow-on questions, you can drill down to what you're looking for. And I think that's the critical difference there, is the ability to ask a follow-on question. That is more important than being able to state everything in a single query. And that's one of the things that, one of the reasons why a more flexible and less precise, more flexible, more informal, and less precise knowledge graph can get you somewhere that you wouldn't get to with an ordinary question, with an ordinary query language.
Thank you.
Okay. With that, we will adjourn the meeting, and I hope everyone can come next week to the Matthew West talk. His slides are already posted on the meeting page for next week. There's an abstract for the meeting, so looking forward to seeing everyone at that meeting next week.
Okay, and by the way, I think what I'll do, I always appreciate getting these questions, because what I'll do is add a few more slides to this note, and I'll add those slides after slide 8, so that the first 8 slides will be unchanged, or I might change some of the make some little corrections on the first 8 slides, but then I'll add some more slides after slide 8 to deal with the kinds of questions that Ravi and Todd were asking, and those help hone in on issues that I think need to be explained.
Okay, great.
So I'll upload a new set of slides later.
Thanks, John.
Later this week.
Thanks to everyone, and see you all next week.